So I think my screen is visible. So let's start the quiz session. So let me just first go through like what are the questions which are given in this week. So just go to the. So as you can see that however the week 6 is all about uh, when the design of exoskeleton and how different control strategies like force control strategies, neural control strategies, so how different control strategies have been implemented. But if you look at the assignment questions, most of the questions are they're basically this comprehensive type. Okay. I mean, it has been done purposely because the part which uh, broadly week six cover is basically the research part which Professor Felix did in during their PhD and also currently they are doing. So they are going too deep, but as far as the course is concerned, you please focus on the comprehensive part. I mean, I'm not asking you to like. So let's just like I will give you some kind of a perspective here that I so like let's see. So this is the first lecture of week six, I think, right? So in the week six first lecture, you will see those. These are some of the. So this is basically literature review. What is exoskeleton? So please go through this. Please go have an idea, right? I mean, don't learn by heart, but try to understand stuff here. Okay, so like what are exoskeleton? What is endoskeleton? And yeah, so like just give you so like when you go for exam just give a readout. Okay, you don't have to remember it but just give a readout for this. So this is basically the what is the history of exoskeleton, right? How they have been developed. Okay, so you don't have to go through like just need to know Hardyman the name, right? Because these are because in the final exam also you will get to answer this multiple choice question. Okay, you don't have to remember those big name also, but just you need to know just to hear this name, you just need to know that there is a Hardiman named exoskeleton which was developed by something like a GE, right? So there's leaks and because these are like just need to learn, you just need to like know that these things are there. Okay, just you don't need so there is no such concept is involved in this. Okay, it's just data there. Okay, so but regarding your exam, so most of this uh, yeah, so these research they have taken it from some research papers. So you can see the you can see the references also. It's just if you go through one of them, just a Google page, right? So so the course is designed like that. So it's not like it's not completely taken out from a book, but you can just Google search this thing. Okay, there is no such thing. So please have an overview, but don't spend too much time on this slides. Okay, and let's go to the there's week five. I'm talking week 26. If you go through so week 26, the half lecture about I think it's half right. So most of the week six is also covered the exoskeleton part, but specific to hand exoskeleton. So you don't need to remember this name. Okay, there are too many. There are too much names involved here. So please don't remember it. Plus, but please do remember it. How the hand exoskeletons are classified, right? Because these things can be asked by any of your comprehensive type of exam. So I think I don't know about this part, but yeah, you can see that that type of exoskeleton do not use batteries or actuators. These kind of questions are specifically wanted to test like what this powered exoskeleton means, what is passive exoskeleton, and what is pseudo passive, and all those things. Okay. So please do know like these names. Okay, these the classifications, right? Please do remember this and you don't need to go through like why this particular exoskeleton is doing what this because there are too many of them. Okay, so it's very hard to remember. So please make a choice. Okay, so it's just for your information. Okay, because I mean there are too many, there are too much of them. So like if you and please do so this the cable driven and direct driven mechanism. So please go through this slide. So I mean you can easily remember it. Okay, there is no such big uh, there's, there's no such big science here. Okay, so you can please remember this. And these are some of the experiments which professor have did, so you don't have to go through it. This is generally for your knowledge. Okay, you don't need to remember this thing issues, design challenges. So like yeah, so you can remember these things. What are the problems which faces, right? The free finger, and also one of the most important requirement in the hand is safety. These kind of things, please go through it. Don't need to go through the design itself. So the conclusion part, so always go through the conclusion part. Okay, I think in every lecture slide you will find one conclusion slide. Okay, so if so conclusion and introduction part, please go through it first. I think I would suggest you to go through. Let's say let's open. I think week 26 is already open. We need to go through lecture 27. I think. So if you so please go through the outline part first, and what you should do is I think there is no such conclusion part here. Don't have to go through the conclusion part because these are experiments. Okay, you don't have to remember these values. Okay, we won't ask you this question. Okay, what is the but please do remember the conclusion part, like what. But I think here Professor Felix have forgotten to add that part because this is basically the result part. We want you to remember conclusions. This is result continued only. Okay, so please don't because that kind of questions won't be asked in your exams. Yeah, here just just go through the outline first, and I think here I think you'll find this conclusion. So yeah, please go through this conclusion part. Okay, and after that you will decide if you want to take this part or not. Okay. And these things, I mean, you don't have to remember this long differentiation, but you do need to remember this how you get this Lyapunov function, and what are the steps you need to do after, like, because there's v dot, right? You just need to stabilize stuff. So the v should be greater than 0 and v dot should be greater than 0. So that means the system is asymptotic. So please do remember this condition. Okay, so that kind of questions can be asked in your exam. Okay, and you don't need to go through it. I mean, so that is a general idea which I wanted to give you before starting the today's session. I think week 7 is also about the experiments and the simulation which Professor Felix did in their PhDs, or also in their currently what he is doing right now. Okay, so you don't have to go through deep inside it because um, that is the research part. Okay, just please do go through the conclusion part, what you can get from those experiments or a simulation part. I think we will start the today's session. I think yeah. So I have designed the session today's session also on the comprehensive lines. Okay, so please yeah. So I think you can see that which finger joint is responsible for flexion extension motion. You can easily get this part. Okay, okay. There are so please do go through this biomechanics part. Okay, what kind of joint muscles? I think we are not using cable driven things, so you don't need to go through the muscles part, but please do go through the there is only three joints: PIP, distal DIP, and MCP. Okay, so please do go through like what are the functions of it, and also the thumb joint. Okay, so there are in thumb also there are three joints, right? Please go through what those joints are called. Okay, that is the biomechanics side which you should know. Okay, like that. We'll start the today's session. I've also made some questions, but these are on the same line. These are very simple questions. If you have any questions, please do ask. You can unmute yourself and you can ask a question to me. But or what you can do is you can type your questions in the chat box like this. Okay, you can type it here and you can send it to me. And for like I think for I think weeks in week 5. I don't know about week. yeah, so from week 5 or a week 6 onwards, uh, the books you need to refer is, I think there is no particular book from week 5 to week 7. Okay. If you go to this course, what the course? If you go to um, this is an announcement section, and what the course question is. Okay, so if you so for the books, I mean, for I think from week 1 to uh, week week 1 to week 5, I think you can depend on these two books. Okay, you can refer any one of them. You don't have to go through both of them. You need to refer only one of them. And for, let's say, uh, for Lakshmidhar Behra, okay, so intelligent systems and controls. So so this book, I think this is specifically for controls part. Okay, so I won't press completely on the, so specifically regarding the control part. Let's say I think we are talking about this in week 7, right? No, I think it's week 6. Week 6 is all about those neural network things, or those force impedance control kind of stuff. So for that, I would refer to go through this book. And these are, I think these two are the research papers. If you're interested in the research, please go through it. You don't have to read all the part of that. Okay. So in this manner, you need to prepare for course exam. Okay. And I'm not on the course exam, but if you find any difficulty, you can always ask us the questions. But yeah, but starting from week 5 onwards, week not week 5, week, yeah, I think from week 6 onwards, most of the questions are based on this comprehensive based only. Okay, so you don't need to go in depth into that. Okay. So let's start the today's session here, and that was a small announcement which I have to make, and I think we start. So the first question is about the main function of robotic exoskeleton is. So anybody want to answer this? So I think yeah, so robotic exoskeleton, the first main function would be, because most of these exoskeleton, uh, because what exoskeleton do, it enhances the performance of the wearer, right? Or if you go through the medical thing, then it enhances. Or if you go to, let's say, in the military things, in the military domain, then there is something called protects your body also. And there are so what are the main function it needs to do? So the first function, the robot exoskeleton should be taken care is of safety. Actually, it's not a, but in the option it is given protection. So protection is, I mean, almost similar to kind of a similar words, right? Protection and safety kind of thing. So for this kind of thing, you just always need to refer this lecture 25. I think lecture 25 you will find what are the main functions of an exoskeleton should be. So, so yeah, so these are the four main functions. Right? Support the physically disabled patient. So that has an application on the medical domain side, and then there is a protection. It protects the body. So please remember this all four things. Okay, support, protection. Okay, so protection is basically the safety, and then enhancement, providing strength to the human, or the wearer, the operator, sensing and fusion data. But but when you design something like an exoskeleton, so what you should need to consider is, like, so this is the conclusion, or I think the pressing issues of the design challenges. So yeah, so the one of the most important requirement in the hand exoskeleton design is safety. I think it is applicable for every joint. Okay, not for only specific to hand. Because let's say if you're making a knee exoskeleton, then also you should take care because those motors are can like I mean yeah, it can bend your knee also, right, in an human manner. Okay. So the safety is the one of the pressing issues. Okay, so let's say if a question is asked like let's say if there are multiple options and in the question it is given choose only one. Let's say protection is also there and enhancement is there, protection, enhancement, and let's say support is there. And you wanted to choose only one, then you will only choose the first preferable choice will be protection or a safety kind of thing. Okay, so because that is the protection is one of the main objective of a robotic exoskeleton, protect your body or it support your body. So when you design something, so the question say that what are the main criteria which you need to consider while designing an exoskeleton. Your answer will be safety. Okay, so safety is the first thing which you need to make sure ensure that okay that the developed device won't kill you or won't affect you in some unhuman manner. So coming to the second question, so a four-bar mechanism based finger exoskeleton is preferable than a serial link based finger. Okay, so, so there is a question like why we have chosen the four-bar mechanism. Okay, so like instead of choosing something like so like this is the PIP metacarpal and I think let's say this is so instead of so the question is asking like instead of making uh, this is your tip actually. This, instead of making a serial link based manipulator, right? Why? So instead of like let's say there is a motor here, there is a motor here, there is a motor here. Rotate your finger. Instead of making this because this looks very simple, right? Why we have move on to let's say like a four-bar mechanism. So that is one of the question, right? I think I have not. Yeah. So this is kind of a four. So like so for 1 degree of rotation, we are using let's say a four link, whereas in this case we are using one link only. Okay, so why we have chosen this? Okay, so what will be your options? Be lightweight, compact design, accurate tracking. So lightweight, I don't think so because I think four mechanism has more links, right? Than compared to a serial link based manipulator. So it has actually more weight, right? It has a disadvantage. A option is wrong. Compact design, no, I don't think so because it's very complex design, right? You can see that. Or is it C or is it D? For that, for this kind of questions, you need to go through those lecture slides. Okay, so like let's go through it. Let's find out if there is any something given in those slides or not. But then you already know, right? I mean, Professor Felix have used those models. Like why we have chosen those models. So I think it's not given here. So like this is the I think, yeah. No, I think this is again. So this is 28, like 27. If you go through those lecture again, the objective understanding human. So I mean, why we have chosen? So like you can see that the motivation. So in this slide only you can get your answer here. Okay. So like human finger joint cannot modeled by a single revolute joint because changing instantaneous setter. Because I think if you look to the physiology or the anatomy of a anatomy of your phalanges or distal phalanges, I need to draw it and so that you will understand. Let's say this is something like a bone here and this is your this is something like okay. So this is how your joint look like. Okay, so it will bend like something like it will flex, right? So this is so your joint has something like yeah, it has something kind of ellipsoid, right? It's something, there is a depression here, and the depression, and this is something like a bulgy part, right? And it forms something like a uh, for this point, I think it forms something like a ellipsoid joint, right? So please do remember this. So what kind of joint? So you see those physiology. So so the physiology is basically your center of rotation doesn't always be constant. It's in the center. So I think this is for finger, but I will explain you what happens to the joint, something like a knee joint. Let's say this is something like a knee joint, and there's something called a patella joint. So when you bend something like it, so basically your center of rotation is something here. Okay. But when you bend your knee, center of rotation actually it not only rotate, but this this femur also translate. Okay, so this is a femur and this is your so this is basically your knee joint. Okay, I'm talking about. So this is basically your thigh part, your shin part. So when you do this, it not only rotates stuff, right? It not only rotate about this point. Okay, it also rotate, but it also translate. Okay, so this femur will go backwards, which is actually posterior, right? Posterior to your tibia when it bend. Okay, so what happens is your instantaneous center shift. Okay, so so that's what Professor Felix was trying to tell here. In finger also you will find this kind of thing. Okay, so it cannot be modeled by a single revolute joint because changing instantaneous center of rotation because center of rotation changes. Okay, so hence four bar mechanism based finger extension is designed. Okay, so that's why they have designed four bar mechanism because if you look to the four bar mechanism, it always changes center of position, right? I need to explain this part also, but yeah, I think let's say this here. Okay, so I think this is where your joint lies. So you see, this is also rotating, but this is also moving in translate. So this is also translating and also it is rotating, right? So it can serve as a something like can serve as a phalangeal or a joint which is translating and also rotating. Okay. That is that. So that's why they have chosen this four-bar mechanism. Whereas in case of something like this, something like a serial joints, so the center of rotation always align with the motor shaft. Okay, it not change, not it's not changing always. So that's why C is your answer. Okay, so please go over this kind of lecture like motivation, something like a bullet point kind of thing. When you find it here, please go over this. Okay, don't have to remember these complex equations. Okay, because these are you don't have to remember this. Okay, but we won't ask you this kind of thing because this is too much complex and this is basically research part. Okay, so you don't have to go through it, but please do know like why we are doing it. Okay, please do know the reason like, why we are doing it and what we will get and what is the advantage compared to what we want to do, right? Please have an idea. Okay, so please don't go through this. Okay, and just the equations, just be that way. And I think there is no such kind of a conclusion part, but please go like work volume, right? Please work volume is basically how much the workspace this whole mechanism can cover is what they are trying to tell you. So please don't. And okay, so this is question two, and let's move on to a new question. So yeah, so this is the same expression based question. Okay, I forgot to. I think yeah. So the expression for relationship between joint torque and end effector torque. I think you already know this term, right? Torque is So basically, Jacobian is something which maps data from joint space to maps data from I think it's maps data from joint space to joint space to end effector space, right? End effector base, right? That is what the joint space do, right? Torque. So basically, it's already know it, right? Tau is equal to J transpose into F, where F is the end effector force, and I think tau is the joint torques, right? So B is the right answer. I think I don't have to give much more explanation to that because this is one of the basic questions, and I think not the answer. So in the force control experiment setup for finger exoskeleton, where is the force sensor placed? Okay, so these are some generic questions which you should know. You should know like how the experiment setup has been placed. Okay, so for that you need to go through those slides. Okay, so let's open that slide and see where those setups have been. So this is how you have you need to solve those questions. Okay, you don't need to go through the lecture again, but plus please go through those slides. Okay, lecture slides, that is important. Okay, so this is some kind of I think force control strategy. I think it's an impedance based control strategy. But yeah, you see that they like you can see the experiment setup. See that there's the this is a graph object. There is this force sensor. This is called FSR sensor. You can easily buy it this sensor. Okay, these are easily available. So these force sensors are placed inside an object to see how much amount of compressive force has been how much amount of compressive force is being applied to the object using this exoskeleton. Okay, so based on based on that force only will uh, you will apply for position. You will give position to those actuators, right? Operated actuators, because if you apply more action here, then there is a this force will be higher, right? So we need this force sensor to see like how much contact force is happening, so that we can tell this actuators or motors, so that that object, so that we won't get that high force. Okay, so here in this case I think we are trying to capture this object. Okay, so I think but most of the experiments are done by grabbing that coin. Okay, but if that force is high, uh, then there might be a case that your finger might break. Okay, because you are applying two opposite force. Okay, more compressive. So that's why these sensors has been used, the force sensors. So yeah, so in the force sensor setup, where is the force sensor placed? On the exoskeleton tip, or on the object, or on the human? So what do you think? While looking to that picture, what do you think? Like where should we place it? I think where should we place it? So in this case, what they have done is, I think if you go through the lectures, Professor Felix has said that they have placed it in the they have actually placed on the surface of this glass object. Okay, but you can also place this on your exoskeleton tip. Okay, but for the experiment, they have placed it on the object. Okay, on the human, no, I think you don't can't place those on the human. I mean, why would you need to place in the human? Okay, because you have that exoskeleton, right? So your option is B is B is your right answer. Okay, let's move on to our next question. So why unsupervised learning mode is preferred over supervised learning mode for robotic inverse kinematics based control of redundant manipulation? Yeah, so this is the question which I think Professor Felix has also been. This is one of the topic which Professor Felix has also been stressed in. I think it's a topic about week 29, or I think it's week 20. I think it's lecture 29. So if you go to this lecture 29, you don't have to. I think that this case-home architecture, it's very complex. No, so you don't in this. If you want, you can go through this, but if you are unable to capture this part, I think, but you can capture this thing. Okay, I think this is one of the lecture. I think this is a. I think this was covered in week 5. I don't think so. I think this was covered in week 5. Okay. So I think you can get through this. So there are these two conditions, right? Because for a redundant manipulator kind of stuff, right? There are yeah. So like here, I think if you go through the lecture, we have introduced this something called unsupervised learning, right? Unsupervised mode, and he also given those why he move on to those unsupervisory mode, right? So first, let's say first read it. So alternatively, the inverse kinematic relationship can be directly learned in unsupervisory mode by actuating the robot. So first you need to learn this part. Okay, first you need to read this part. Why we have gone through it. So like forward kinematics is a collected at a random joint angle. The neural network is trained by supervisory mode. So you know that a neural network is there, right? Because there is an input and output. You can easily get it because there's something called so I need to first read this thing and then I will explain like why we have move on to that part. So like the neural network is trained in a supervisory mode to learn either the forward map or the inverse map. However, for redundant robot, the inverse kinematic relation cannot be learned directly with the data since it's one to many relationship. I will explain you why this is there is one to many relationship. So and let's just read this part. Alternatively, the inverse kinematic relationship which we got it, which we are facing issues, right? So alternatively, the inverse kinematic relation can be directly learned in an unsupervisory mode by actuating the robot with the joint angle configuration generated by neural network. So we need to actuate the robot with the joint angle configuration generated by neural network and adapt the neural network itself for position reached by the end effector. Such approach resolves redundancy in the learning phase. That is what it was trying to. So let's just explain this statement to you. What he tries to mean here. Let's say uh, you have this two joint, right, and it has been fixed. So I think so what is the degree of freedom of this joint? Like one, two. So if you want to know this position orientation and let's say angle is also given, then you know that the joint angle configuration is equal to the end effector. The joint space is the 3 degree of freedom, whereas the end effector phase or the this is basically a joint space, right? It's joint. There are three joint spaces, whereas this is the end effector space or basically the Cartesian space. These are called Cartesian space. The joint space has only rotation. So since this is only W joint, so there is only rotation involved. Whereas for a Cartesian space, which is also called end effector space, the position with respect to the fixed frame as given, okay, and which can be x and y, and let's say the two theta is also given. So we have three variables here, and we have three joints. So the joint space is also have these three variables, so which is equal. This is something called so this is non-redundant system. But let's say if you have something like a four joint, okay. So the joints has four variable, which is q1, q2, q3, and in the right hand side you have only x, y, and theta. This theta is basically the orientation with respect to the fixed frame. So you have x, y, z here, and you have this q1, q2, q3, q4. which is actually, so you have Q1, Q2, you have more degree of freedom in the joint space, right? So this type of systems is called a redundant system, right? So which means that in order to reach something like this position, you can do this by this method, or you can do this, can reach it like this, okay? Something like this. So there are multiple solution to so there are multiple solutions, right, to get this thing done. So forward kinematics, you can easily get it, okay? If forward, what do you want to, in forward kinematics, what you will do, you give this q1, q2, q3, right? Q1, q2, q3, q4, and you will get something like x, y, and theta. Because you have those equations, you can easily get it. But this is forward kinematics. Whereas in inverse kinematics, that is a problem here. Okay. I think if you get this, you can easily train it also. So for training something like a neural network, you need input values and output values. Input values are basically Q1, Q2 values, okay, and X, Y, Z value you will get it. Okay, so you can easily do the experiment and you can get. You can just say robot to move Q1, Q2, Q3, and you will get some X, Y, X, Y, Z, X, Y, Z, and make a table out of it and train your neural network, right? But let's say if you're doing something like an inverse kinematics model, and you can get those equation, and when you give something like x, y, theta, in that case q1, q2, q3, you will get multiple solutions, okay? So when you give x, y, z as input, you will get something like q1, q2, q3, you will get multiple solution, okay? Then it will be difficult to solve a supervisory neural network model. For that only you have used something called unsupervised learning, right? So your option here will be to resolve redundancy. Okay, that's why we have used this, because this is an example of a unsupervised. This is an example of a redundant system. Okay, so that's why we have to go through those. That's why A is your right answer here. I think we have three more questions, and I will grab this thing. What are the features used for biosignal based neural control for exoskeleton? I think I mean, there's no Pujort. Pujort parameter is the only parameter which you can get. I mean, Fleming, Kingsley, so there is no such parameter which has been mentioned here. So please, for referring this kind of, I think lecture 29, or is it lecture 30? I think it's so I think it's, so this is the week 7, and yeah, I think it's week 30. So in week 30, if you go through those slides, you will get there are these are the parameters, right? So there is the activity parameter, mobility parameter, and complexity parameter. So please do remember, you don't need to go through like how they have calculated, but please do remember this part. Measure the variance of the timing data. What it do, it measure the variance. Mobility, what it do, it define the square of the variance. So represent mean dominant frequency. So this is what mobility means. Represent mean dominant frequency. And what its complexity refers. It measures the similarity of shape of a signal to pure sine waves. So please go through this three features. Okay. Please don't remember this. I don't think, but please have a overview like how all these three equations are different from different across these features. Okay, how this has been different from. Please have an idea about that. These all these parameters are called Hojor's parameters for EMG activities. Like these activities, so this is the raw data, and based on some kind of a processing, you will get the actual EMG data. This is the how an actual EMG data look like. I think you you zoom this out, this is an actual angle. So this is not an angle. So this is angle basically, but they haven't shown how the EM after post processing these angles look like. This is how the data you will get, but you need to do some kind of a post processing. For that, the professor have used something like a some kind of a interface, EMG kind of interface. I think if you go to the video, he briefly talked about that. Okay. So A is your right answer here. Moving to the next question. What are the biosignal parameters used in our studies? So there is only two biosignal parameters. There is EEG, which is I think a brain-based signal, and there is EMG, is electrode-based. Uh, okay. So these are something which you need to take in mind. So this is like a EEG cap, which so I think you can see this is a user it's wearing with EEG. There is only these two different signals, two different kind of sensors which they have used. And coming to the last question, how many degree of freedom the optimally designed three finger exoskeleton has? So how many degree of freedom the optimally designed three finger exoskeleton has? Any idea? So for this kind of thing, again, you need to refer those lectures. So this lecture is based on I think it's week 27. Because in week 27, if you go through it, so they have used this optimization for bar mechanism, and here for a brief period of time they have referred like why they have chosen a 10 or a 8 degree of freedom. You see this is what they have used. Okay. So if you the methods part for the index finger, they have used 3 degree of freedom. For middle finger, they have used 3 degree of freedom again, and for thumb, they have used an 2 2. There is a abduction adduction and there is action extension, right? So I think it should be, yeah, but I think thumb 3 3. Index finger, for index finger they have used something called a ellipsoid joint. So ellipsoid joint has a 2 degree of freedom, and there is a hinge joint which has 1 degree of, okay. So 2 degree here, 1 degree here, and again there is a saddle joint. Saddle joint has I think 2 degree of freedom. So you can see that kind of rotation. So there is two kind. One is the longitudinal and one other one is the lateral direction. Whereas hinge joint has only 1 degree of freedom. That's what has 2 degree of freedom. So let's consider the index finger here. The index finger, right? So how many joints we are considering here? We are considering one here, which is the left shoulder, 2 degree of freedom, and then there is a hinge joint here again, right? 1 degree of freedom again. So index finger has total 3 degree of freedom. Similarly, middle finger will have 3 degree of freedom. For thumb, they are saying 2 degree of freedom, abduction, adduction, and there is a flexion action. 6 plus 6 plus 2. So I think it's 8. Yes. I don't know why they have taken. So not given here actually. They are saying 3, 4, right? Optimally designed three fingered exoskeleton. So here they are asking for the optimally designed exoskeleton, but we are talking about here it's not optimal here. Okay, the method of finger capture but if you go through this lecture, it's not optimally designed finger. Okay, for optimally design, you need to go further more. Okay, so using vision. So basically, the position for a four-part mechanism, position of mechanism, the position. Yeah, I think you will find this here. Optimal 4-bar mechanism. Okay, so for this thing, you need to dig deep here. Okay, so they are trying to reduce the error here, which is basically HI minus I is the path of a human data and path of a 4-bar coupler. And here, I think this is what they have used. Okay, so if you go through this again, serially 4-bar mechanism. So 4-bar mechanism, if you know, each 4-bar mechanism has 1 degree of freedom. There is a proximal 4-bar, middle 4-bar, and there is a distant 4-bar mechanism. Okay, so similarly, what they have done is there are three 4-bar mechanism for finger. Again, then there is a three, then there is a two, I think. So this is a proximal part. There is a middle part, then there is a distal part. Okay. So how many degree of freedom? Two, three, three, again three, three. Again for thumb it should be two, right? But serial unit of 4-bar mechanism current middle finger again, and the proximal is 4-bar, middle finger is 4-bar, and distal is 4-bar. Serially connect. I think the answer is eight, but I think but it's not been written here. I think it should eight. I should be eight, but it's not written here. I will check and I will let you know. Okay. So please take a hold on this. Okay. But yeah, I think this is all. This is about this week. If you have any question, please do ask. Okay. You don't need to go through deep into those research aspect of the lecture. Okay. I think it's high time. It's 7:53. I think I will stop here.